already have done lab exam also. Here heterojunction means different band gap material if you form. Okay, different band gap material. How heterojunction form means heterojunction laser or diode whatever. Okay, by different band gap materials. Okay, when you combine two different band gap material, heterojunction will form. Okay, that is what heterojunction means. Okay. So here, suppose if you take here gallium arsenide, p-type. Suppose take here p-type gallium arsenide. First we will see p-type construction, gallium arsenide, and here also again p-type aluminium gallium arsenide. Okay, and on the top you take one more layer. Here it is n layer. Okay. Okay. Or otherwise you can any direction you can take it. It's not a, you can take P layer top side or N layer down side. You can take that way also. It's not a problem. Okay. Aluminium gallium arsenide. So here aluminum gallium arsenide band gap is about 8 or 9 electron volts. This gallium arsenide is 1.4 electron volts. Here also 1.8 electron volts. This structure we are calling double heterojunction. Okay. Double heterojunction, or you can take two different band gap also. You can take it. The double heterojunction. So here you will take the metal contacts again. Okay, here you will take the metal contacts. Here also you will take the metal contacts. Then you will apply some biasing voltage here, forward bias voltage, and from there electron holes recombine. Then we will get the laser output. Okay, here how we will take mainly, here we will take the metal strip geometry. We will take, what is the strip geometry we will see. Okay, just I am drawing again here. What is the strip geometry? Let's discuss. This is top layer. You can take P layer also, it's not a problem at all. P type aluminium gallium arsenide, and here this is the active layer. Okay, another P layer, here gallium arsenide layer. So here this is 1.4, this is 1.8, and here downside N aluminium gallium arsenide. Okay, N type and P type. Okay, so here again we have a metal contact backside. So this is metal contact. Here you can take metal. This is any metal you can take. So strip contact means top side will take a metal like as a strip. Okay, just like this. This way we will take the metal contact. This is the metal. Okay. So what is the use of this strip contact? I will tell you. Okay, this is also metal strip. Okay, metal strip. Okay, because of this metal strip, only that much width only will get the laser beam. Okay, only that much width of laser beam will get it. Okay, like this. There is a active medium. In this only, this much only will get the laser beam. Okay, this much of laser will get at the interface layer. Like that, we are reduced the width of the laser using this strip. Okay, how much width is this strip? Just like a 0.5, like that, 0.5 micrometer like that. Okay, so this much only will get the laser from the active medium, or from the junction will get this much width of laser beam will get from the this material using this structure, this kind of structure. So what we will do, backside again we will cleave this surface or polish this surface. Okay, polish or cleaving. Okay, polish or cleaving. Okay. That means suppose light is propagating 110 direction, perpendicularly we will polish this one. Okay, light cannot enter this side, and front and back side also we will rough this surface, so light will not come this direction, only one direction, only this direction light will propagate, or laser beam will emit from the only this surface, front surface. Okay, it's a right side surface. Okay, back side will polish, and front end back side will rub the surface. Okay, and top and bottom already metal contacts are there, light will not go that side. So only now face is front side, light will propagate. So using this strip only we are reducing the width of the laser beam. So if you reduce the width, it will be focused, fine focused beam will get. Okay, that is the use of this strip contact. So here this p-type gallium arsenide is the active medium. Okay, these are the just to create the band bending. Okay, so now we will see the, this is simple construction. After that we will see how it will work, what is the advantage of this heterojunction, so why we are using. So in homojunction, electrons will diffuse one semiconductor to other semiconductor. In the p type it will diffuse, so electron hole recombination takes place, and holes also diffuse in n type. Because of this one, holes electron will diffuse. Because of this diffusion, we will lose some charge carriers. Okay, that output power will reduce. So using this one, we can trap the electron holes in a particular region, and we can improve the output power. Okay, is it clear? Clear guys? Construction.
Sir, once again.
Yeah, okay. So here what we will do, first one, here first top layer will take the metal layer. So just I am drawing just like a try to draw three dimensional. Okay, first we are taking, this is a already three layers are there. Okay, just a minute. Yes, I will explain. So earlier we have taken only two layers. So N layer, P layer. This is N and P layer. Here what we are taking, so in the middle, because in this layer, homojunction layer, some losses are there. To reduce the losses, we are taking heterojunction laser. Okay, here heterojunction means here N, again here P layer, and again top also P layer. But this band gap is 1.4 and top band gap is 1.8. So these two are making one junction, and downside also 1.8. These two are downside two also making another junction. So that's why we are calling double heterojunction. Or you can take only different, okay, aluminum gallium arsenide here P layer, and N layer you can take aluminum gallium arsenide. Okay, this is 1.4, this is 1.8. So this way also you can make the laser. Okay, two layers, just you can make here metal contacts, here also metal contacts. This way also you can make laser, but this output is very less. So that's why we are going double hetero structure. So first how we will construct, first we will take the n type layer. Okay, here that is n type layer, n type aluminum gallium arsenide, aluminum gallium arsenide. And in the middle, active layer we will take. Okay, active layer, this is P type gallium arsenide, gallium arsenide. On top of P layer, one more layer will take. This is again P type aluminum gallium arsenide. Okay. So here these layers we have taken. So after that you take the metal contacts. Downside again we are taking some metal contacts to apply biasing voltage. Okay, without biasing, without metal contacts we cannot apply biasing voltage. If there is no biasing voltage, we will not get the laser beam. Okay, so we are following special structure here. What is the structure means? Here earlier we have taken just like a grid electrodes. Here grid, right? So in this case what we are taking, strip, just like a strip electrode we are taking. So this is the strip. This much only will coat the metal layer. Okay. So the use of this strip is, just see here, this again I am drawing front side these layers. Okay, just like this one. Okay, just like this one. So because of this strip, so when electron hole recombine in the active region, okay, active region, we will get the photons, right? After photons, this will emit from the front side. So using this strip, this much width only we are applying the bias. Okay, this much only. This is like a zero 0.5 micrometer. Okay, only 0.5 micrometer width only we are applying biasing. This is front side electrode, this is back side electrode, this is back side, and this is the front side electrode. Okay, in between these two electrodes we are applying some biasing voltage, forward bias voltage. Okay, so far this is forward bias. N type is connecting to negative terminal, and P type is connecting to positive terminal, like this. Okay, so light, after emitting light can propagate any direction. So we want only one direction. That's why what we'll do, this back surface we are polishing this one. Suppose light is propagating in 110 direction. Okay, 110 direction. perpendicular to the one direction, we are polishing the surface. Okay, polish. Okay, so that light will not go backside. Light will only enter into front side. And one more, total six spaces, right? Down, top, left, left, right, and front, back. Okay, so this side also we will rough the surface, front and back, front and back, and right side only laser beam come. Okay, in this only this much width only laser beam will emit, because we have made a strip here. Okay, this much of laser light will come. Okay, the width is here, how much width is 0.5 micrometer. Here also you will get uh, laser beam output, width is 0.5 micrometer. Okay, because the advantage of this strip is we can reduce the laser beam. Suppose if laser beam is spreading very long width, it will be not focused. Okay, it is intensity is very less. If it is very fine, we'll get the very high intensity. That's why we are using the strip contact. Because of strip only we get fine, means focused beam we are getting. Width, we are basically we are reducing the laser width, and we are increasing the intensity and focusing. That is the use of this strip. Okay, so this surface also we are rough. Okay, so that only this front surface only we will get the laser beam. Remaining all surface we are blocking. Okay, so is it clear now? So
Yes, sir.
after that we will go to the band bending diagram. Then we will see we will understand how it will work. Okay, so first we are taking here p type, right? P type means here take a huge large band gap, and here small band gap. Okay, small band gap, again here large band gap. This kind of structure is there. This is 1.8 electron volts, this is 1.4 electron volts, and this is again 1.8 electron volts. This is P type aluminum gallium arsenide. This is P type again gallium arsenide, and this is N type aluminum gallium arsenide. Okay, this way we have here, see, this is the different band gap. So how it will form means, just you combine this one. I will draw it again. Okay, just you band bending diagram, just a little bit difficult here. You can see here. So it is just like, there is a some interface, just you can draw like this. Just as, so just like this. Just a minute. So here you can see the band bending. So this is a p layer, and this is 1.4 electron volts, this is 1.8 electron volts, again it is 1.8 electrons. So here we are giving, this is p layer, again this is n layer. So here we are applying forward bias, so like this. So when you apply some forward bias voltage, this holes will move towards this layer. Okay, holes will move, and here they will see high potential barrier height, and here we are applying negative potential because of this one electrons. Okay, here electrons are there. These electrons will come here. Okay, electrons will come here, and these electrons will see whose potential barrier, they will not move forward. Okay, they will return back again. Here also holes will see high potential barrier. Because of this potential barrier, holes will not move into n layer. This will return back in this active layer. Okay, here this is the p gallium arsenide is the active layer for in this heterojunction laser. So what is happening here? Because of this heterostructure, electrons are not diffusing into p layer, and they are returning to again same layer, active layer. And downside also, holes are not entering into n layer. So electron holes are trapping in only this active layer. So using this heterostructure and using different band gap, we are trapping the electrons and holes in the active medium only. Okay, so that we are reducing the recombination losses, or we are reducing the electron diffusion of electron into p layer. Suppose if electrons will diffuse into p layer, these holes and electrons will recombine, so there is no useful of this one. So after trapping electrons and holes in this active layer, this electron jumps from conduction band to valence band and they will recombine. Because of this recombination, it will emit the photon. It will emit the photon. Okay, like that. Earlier also we have discussed last class. So higher energy state electrons, they will jump fast and they will emit the spontaneous photons. Here also you can see different states. Here also you can understand this way. Okay, like this states are there, different states are there. Okay, so higher energy electron first jumps to the jumps and it emits the spontaneous emission and spontaneous photon. After that they will trigger the remaining electrons. Okay, like this we will get the things. Okay, or you can see this way. When we discussed this 1.8 and 1.4 and 1.8, so this is the band bending diagram. Another way we will understand here. So this is the high band gap, this is the low band gap, and another is high band gap material. Okay, you just join this one. Okay, just you join like this. Okay, just you join. So now here you are applying a some forward bias voltage plus and minus, and here is the p type aluminum gallium arsenide, and here n type p type gallium arsenide, and here again n type aluminum gallium arsenide. Okay, so wait, I will draw a bigger diagram, then it is very easy. Okay, here see. Okay, so again it's bigger diagram. So you just join. This is also band bending diagram. This is flat band bending diagram. Flat band bending. Okay, band bending diagram. Here P aluminum gallium arsenide. Here also N aluminum gallium arsenide. Here N P gallium arsenide. So here we are applying forward bias condition, right? So because of this one, whole electrons here. Okay, in the conduction band we have electrons. This will move to the this active region. Okay, and here holes are there, right, in the p-type semiconductor. So these holes will diffuse. Holes will move towards the active region. Okay, now you can see whole electrons are in the conduction band and holes in the valence band of active medium. This is active layer. Okay, so here electrons, suppose electrons want to go here p side, but they will see high potential barrier, so they will return back here. And holes also, they will see high potential barrier, they will return back here. So holes, diffusion of holes will be restricted here, and electron diffusion to p layer will be restricted. So in the bulk region, we are reducing the recombination losses. Okay, only in the active medium only recombinations taking place. That in that way we are getting the photon. So earlier we have discussed this one. Band means it's a number of states here. Okay, like this. Here also many states are there like this. So here also many states like this we can see here. So first this electron, uppermost electron 1, 2, 3, just like first state electron will jump to the valence band and recombine with holes. So once this recombine, it emits the spontaneous photons. Okay, this emits the spontaneous photons. Spontaneous photons. So these spontaneous photons will trigger remaining electrons in the third state. Okay, first state, when first electrons in the first state will jump into the valence band, it emits the photons. These are spontaneous photons. So these photons, so trigger the remaining electrons in the third level. Okay, these electrons again jumps in the valence band. They will emit the photons. These are stimulated photons. So what is the meaning? Now band means it's a number of states. When first state electron jumps to the valence band and it recombine, it emits the photon, but these are spontaneous photon. When electrons in the third state will jump into the valence band, okay. So here it will, who is triggering spontaneous photons which are already emitted. This will trigger the remaining electrons in the third level. Okay, then we are getting the stimulated photons. Stimulated photons. So like that, we'll use the cavity or resonator just like we have discussed, right? Is polishing the back surface and side surface, roughening the side surfaces only, front surfaces only. We are getting the light. That way, we are only getting light one way, and remaining sides we are blocking. Okay, first what we are doing, we are giving some biasing voltage. So highest energy level electron will jump into the conduction valence band and recombine and emits the spontaneous photon. These spontaneous photons will initiate the stimulated emission photons. You always remember in lasers, first when spontaneous emission takes place, here, when spontaneously electron jumps from conduction band to valence band, here photons will emit. These are spontaneous photons. Okay. These photons again will trigger remaining electrons to the comes to the ground state. Okay. This spontaneous photon will trigger the stimulated emission process. Okay. Stimulated emission process. So here again two photons will emit. This is upper level and this is lower level. Okay, like this. So is this clear to you?
Yes, sir.
So it is very easy. Band means conduction band means here band is there, conduction band. Here valence band is there. Okay. Band means it's a number of states. Okay. Here also number of states. Suppose here third level, second level, first level. Here also first, second, third. Suppose in the third level electrons are there, second level electrons are there, first level electrons are there. So here also first level holes are there, second level holes are there, third level holes are there. When third is third state having lesser lifetime, right? Third one T3 lesser than T2 lesser than T1, right? T1 is lifetime is higher. So here electrons in the first state electrons will stay for some time, but third state electron easily jumps to the ground state. Okay, they will directly come to the ground state and they will recombine with holes here. Okay, once they recombine, here spontaneous emission photons will trigger emit. Okay, these photons will trigger these electrons. Okay, electrons in the first state. So this electron again jumps into the valence band and recombine here. So in this process again one more photon will emit. This is stimulated photon. Okay, when electrons immediately interact with holes, spontaneous photon will emit. This spontaneous photons will initiate the stimulated emission process. Okay, that is second one. Okay, so this is happens in every laser. Okay, this is the working of laser. Is it clear to you guys? Working of laser.
Yes, sir.
And population inversion, active medium, and this cavity resonator, these all are same thing, homojunction and heterojunction, but different structure. Using different structure we can improve the output of the laser. Mainly we are trapping the electrons and holes in this way. Okay, only in this way we are trapping in this active medium, so electron will not diffuse into p layer. Okay, this is top, and holes also not diffuse into n layer. This is top, so that only will get the recombination of in this active region only, particular region only we will get the photons. Okay, earlier there is a, if it is band bending is like this. Okay, sorry, like this. So here electrons there is a chance of diffusing into p layer. Here also chance of diffusing into n layer. Here also photons will emit. These photons are not useful. Here also when electron hole recombine, here also photon emits, but this is not useful. So only if it is here, if it in this here region is not specified, but in the heterojunction region is active region is well specified. Okay, well specified. And if you draw the refractive index and profile. So here you can see the 5% difference is there. Okay. Here the first material is different refractive index and second material is different index. So this is just a 5% difference is there. So that we can reduce the diffusion of holes and electrons and we can improve the output. And also we have see, we have specified only this is our active area. This is our active area. Completely we have specified the active area. So that only in this stage then only laser beam come. Okay. Laser beam will emit in this region only. Okay. So that we can know how much region laser is coming, how much intensity is coming. We can improve the laser beam. So what are the advantages of this laser, heterojunction laser? Please tell me. What are the advantages? We have discussed what you understand from laser one, a homojunction laser and a heterojunction laser. What are the advantages? Please answer this one. What are the advantages? If you understand, you can answer. Otherwise, don't know. That means you don't understand. Yes. Please tell me.
More output.
Output is high. Output is high. Second one. So suppose we are producing the laser beam only defined width, right? Because of the strip geometry. So input power is very less. Input biasing voltage is less. Okay. Or less input power is sufficient to give the output power. Suppose if laser beam is producing this much width and this much width. See first case and second case. In second case, laser beam is providing only this much width. Suppose 0.5 micrometer. Here 2 micrometer. Which one required higher power, higher input power? Please tell me. In first case, no. In first one we are producing only defined width only. We are producing the laser beam. So here less input power required. So here laser width is very high. So to produce this much width, you need to apply more power. So that's why here intensity is less, but here intensity is high. So input power also high and input power is very less and intensity high. Here intensity also very high compared to homojunction, and also diffusion also we can reduce. Diffusion of charge carriers also we can reduce. Diffusion reduce. So that we can, so here electrons holes are trapping in the middle layer, right? That's why we can trapping the electrons and holes. The electrons are not diffusing into p layer and holes also not diffusing into n layer, so diffusion can be reduced. Okay, diffusion can be reduced. And what else? So here about you can produce the 10 milliwatt power. Okay, in our so lab also we have used, right, laser. That is there also we have produced like a, when you applied about 1.8 volts millivolts, right? When you applied 1.08 millivolts, laser is produced. So this is very less input power. Then whereas suppose if you use helium ion or gas laser, you are using 10 to 20 kilojoules. So this is high input power required here. But semiconductor laser, you need very less input power. That's why only we are using everywhere. We are using, if required lesser power, you can use these semiconductor lasers. Okay. So any other advantages? Is it clear to you today class?
Yes, sir.
So I will explain again here. So in homojunction, this is homojunction and heterojunction here. Heterojunction means different band gap. Homojunction means same band gap. Suppose this is the, just I am drawing. Homojunction means band bending also very less. Okay. So this is P and N layer. So we are applying forward bias here. Okay. Here when you give forward bias, electron move. This is the depletion. This is the, oh sorry. So when you apply forward bias, Just a second, I'm this sharing is stopped. Let 2 seconds. So in a homojunction, you are applying biasing voltage. This is N. Here electrons, this is the depletion region here. This is the depletion region. Electron move towards the depletion region when you apply negative bias to this N type, and holes also move towards the depletion region. When electron moves to the depletion region, this electron jumps from conduction band to valence band. Initially, they will emit spontaneous photons. These spontaneous photons start the stimulated emission, so that we are getting the photons in this laser. Okay, so here these electrons may diffuse into p layer, or these holes may diffuse into n layer. Here hole and electron will recombine, but here photon emit, but this will again absorb in the bulk region. Same thing in p layer also, hole and electron will recombine, this will emit photon, but this will absorb in the bulk region. These photons are no more useful, only emitted photon in the bulk depletion region only useful. But in this heterojunction, what we are doing, different band gap materials we are taking, okay, like this. So like this, and again here taking like this. So this is p layer, and this is also p layer, this is also n layer. So different band gap, again we are applying biasing voltage here. So here holes will jump from p layer to this p layer, active p layer, but these p holes are seeing high potential barrier. So holes are seeing high potential barrier, they cannot enter into n layer. They will return back to same region. They will return back to same region. Similarly, electrons in the conduction band, they will jump to p layer here. Okay, they will trap in this p layer. This is our active layer. This is our active layer. So when they want to diffuse p layer in this p layer, they will see high potential barrier. Width is height, they are seeing some height, so they will not climb this height, they will return back again. So electrons are trapping in this active medium, and holes are trapping in this active medium, so that here only in this specified region only they will recombine. Okay, where diffusion we are reducing, and laser also producing the specified region. Okay, suppose you want to reduce the width of the laser, you can reduce the active layer width. If you increase the active layer width, you can increase laser output also increase. So here we can change the width of the laser, but homojunction we cannot control. In heterojunction we can control the laser width, and output also we can improve, and also diffusion of the charge carriers also we can control. That is the advantages between advantages of heterojunction layer compared to homojunction layer. Okay, here also same, if you draw output power, this is output power and injection current. So just like you will get the curve, here also you will get the curve like this. So here you can operate even higher temperature continuously, you can operate. Here the heterojunction homojunction layer you cannot operate continuously, and this is you can operate continuously. And here reducing the losses, improving the output, and output laser intensity also increasing. Just now we have discussed, right, advantages. So these are the advantages compared to homojunction layer. Here refractive index is, suppose refractive index is variation is only 0.5 percentage, but here heterojunction it is about 5% difference is there. So here this layer, this is differential index, refractive index, p layer different index, refractive index, this is also different refractive index. So this is 5% difference is there. And here region is not well specified. Okay, the active region is not specified like this, but here in heterojunction it is well defined, active region is well defined. So laser width also well defined, here laser width is not well defined. Okay, you got it right, differences. Is it clear?
Yes,
Differences.
sir.
So once you go through the notes or your books, you have already books, so you will be clear what is the differences between homojunction. Working is same, okay, but different materials we are using, and we are improving the performance of the laser. That's it. lasing action, laser population inversion, and this all are same. Okay, but only we are changing the materials and improving the performance. Okay, that's it. So please go through class, and tomorrow we will start the optical fibers. Okay, optical fiber, that is very important. You can easy chapter, easy second part, that is easy, and you can score easily marks also. Okay, we'll start tomorrow. Okay, then I'm closing the class. Any